Okay. So, okay, since we're only going to have 30 minutes on this round, I think we might as well just get straight into the technical stuff, which I'm excited about. So first, can you give an overall, just general overview of the mission and the objectives of the Milani CubeSat?
Sure. Milani is one of the two CubeSats that will be released in the proximity of a binary asteroid called the Didymos, and it's part of the European-led mission called HERA. HERA is or HERA, depending on how do you want to pronounce it. HERA is a European Space Agency mission that will visit a binary asteroid where we have the main asteroid called Didymos and its little moon called Dimorphos, that will be in turn visited by the NASA mission DART, which is a mission led by the John Hopkins. Sorry, it's John Hopkins indeed. Anyway.
Yeah, John Hopkins APL.
Yeah. In fact, I was even right. All right. So in essence, the entire program, it's a NASA ESA cooperation, is called AIDA, AIDA, Asteroid Impact and Deflection Assessment. So it works this way. There is the DART probe that is going to impact the little moon, Dimorphos, in 2024. And then HERA will follow up 3 years later, so in 2027, at the beginning of 2027, it will reach the asteroid and study the binary asteroid system and, moreover, the crater produced by the impacts of DART with Dimorphos. So in this framework, the European Space Agency included two CubeSats to be released in situ, because I mean you can do some bonus science with CubeSats in deep space. They are cheap. They can be developed in quite a short amount of time, and moreover they are light. So while the HERA spacecraft has to be operated in a very conservative and cautious way, CubeSats can do fancy things around the asteroids. So there will be Juventus with the radar orbiting at low altitude around the bigger asteroid, the Didymos. While there will be Milani, and this answers your question, that will hover in front of the asteroids, because it has a passive payload. It will do some sort of back and forth motion in front of the asteroid. When I say in front of the asteroid, it means in the day side of the asteroid, and trying to study the two bodies in a gradually approaching way. So we will have a far range operation phase in which we are 10 kilometers far from the body, and we will gradually move closer and closer and closer to the bodies, all the way until attempting a landing on the smallest asteroid. So we are aiming to land on the smaller asteroid, and in particular, before that, we would like to take close-up images of the crater, because this will serve the purpose of having a better understanding of the kinematic impact between DART and Dimorphos.
Mm-hmm. Okay, so I'm super interested in learning more about the trades that you had as far as the trajectories that you're going to have around the asteroid. So in the paper that you sent me, there was basically three options you looked at: the hyperbolic arcs, the closed orbits, and the three-body proximity solutions. So I want to get into all three. But first, I'd like to talk about the three-body proximity solution. So basically, is that staying in a way a halo orbit? Because is the gravity of those bodies large enough in order to do something like a halo orbit, especially with the solar radiation pressure perturbation?
Sure. In principle, yes. But there is a but.
Mhm.
So the system is made of this bigger asteroid, Dimorphos, let's call it D1, and the little moon, Didymos D1, and the little moon Dimorphos, let's call it D2. So D2 revolves around D1 in a quasi-circular motion. Therefore, when you have a massless particle, a CubeSat, wandering in this system, you can formally state the problem as a circular restricted free body problem. And so far, so good. The CRTBP has 5 equilibrium points, and 3 of them are collinear, 2 of them are triangular. And the orbits you were mentioning, the yellow orbit, occur around each of the 3 collinear points. They have been very useful to design missions for what concerns observation of the sun, or deep space telescopes at Sun Earth 2. Not even to mention those at the moon, where we have another mission study called Lumio that is revolving in one of these kind of orbits. Now, the issue with the system, and the reason why these kind of orbits were discarded, is that the Lagrange point in this system is located at few meters above the surface of the body. Now, when you're flying a spacecraft, you never know exactly where the spacecraft is, especially if you are in the deep space. Usually you carry out a number of measurements, for instance, radiometric based, in order to solve for on ground for the position of the spacecraft. But even though you have a lot of measurements, usually you are not sure of the deterministic location of the spacecraft. Usually you have a nominal state plus a covariance, which is the locus of all possible points in space where the spacecraft can be. Now, it turned out that if you consider all of this ball around the nominal point of uncertainties, it's like a cloud of points where the spacecraft can be. Well, it turned out that it was not safe at all to go to one of the Lagrange point orbits, because they were so close to the surface of D1 that impacts could not be ruled out of the analysis. And this was the main reason for discarding them.
Okay, that's interesting. So how do you go about categorizing or figuring out what your kind of error ellipse of your position is going to be? Because I think you talked about in the paper there was optical navigation as part of your orbit determination system. So, yeah, so how did you go about quantifying that in that trade?
All right. So in this particular case, we have a fusion of measurements in order to gain confidence with the knowledge of position and velocity of the spacecraft. Milani, Juventus, and Hera, they have a system, and for the first time, they will try to perform a inter-satellite link in an asteroid environment. Okay. Now, there are 3 radios on board. The main one is on Hera, and the other 2 are on the 2 CubeSat. And the 2 CubeSat can exchange with the mothership their information, and as a byproduct of this, for instance, the telemetry and the scientific data have to be relayed on ground by passing through Hera. As a byproduct of this, Hera can measure the distance, so the range between the mothership and each of the 2 CubeSats, and the range rate by Doppler effect. Now, these are the information that you can use to solve for the position. On top of this, as you said, you can include information coming from images that you can take to the bodies, and you can increase the knowledge by putting in the equation also the line of sight, for instance, to certain markers or to certain surface features typical on the 2 bodies. On top of this, we have also a LiDAR, which is a laser altimeter, that can be also used in order to, for instance, to solve for the range to the main body, between the CubeSat and D1 itself. So if we put all of this in the equation, the method that you have to use is the state estimation method, which is typical of the orbit determination step. In our case, we use extended Kalman filters, purposely modified for the application at hand, and we have some quite good results, meaning that we'll have uncertainty that can range up to 100 meters, in just to give you an order of magnitude of the uncertainties that we will have while in the asteroid environment.
Okay, that's pretty cool. So I get it. I want to get into the second option that you had in your trade for proximity operations, which was closed orbits. So is that referring to something like a Terminator orbit?
Also Terminator orbit. Closed orbit were like orbits that revolve all around the main asteroid, so D1. And they can be either equatorial or, as you said, Terminator orbit, which is an orbit that lies on the Terminator plane. Now, why they were discarded? First of all, the equatorial orbits, no way. So we do not want to go in the night side of the asteroid, simply because if you take a picture of the asteroid when you are in the night side, you have no information. And because of the knowledge analysis that I mentioned earlier, you will increase the uncertainty on the state a lot. So it's a risk that we do not want to take. So we don't want to go on the night side of the asteroid. The other strategy would be to put the orbit in a so-called SSTO, Sun-Synchronous Terminator orbit. However, this did not match with the scientific requirements that we have, because we have a payload that is a spectrometer, and the guys behind the instrument, they want to imagine the asteroid at low phase angle. What does it mean, low phase angle? Imagine you are the CubeSat and your eyes look at the asteroid. You want to have the sun behind you, ideally aligned. You want to have the sun, the CubeSat, and the asteroid all on the same line. This would mean 0 degree phase angle. Okay. Now, the guys in charge of this instrument have issued requirements that we have to take measurements at low phase angle. If you go on Terminator orbit, you have 90 degrees phase angle, which is not compliant with the requirements. And that's why those orbits were discarded as well.
Okay. Okay, yeah, so at that point, when you have the instrument requirements. So were there any other instrument requirements, either from any of the instruments that are going to be on board, that also limited these trades?
Yes, still the same instrument. There is another instrument called Vista, which is measuring the impacts of the micro dust particles. It's a high sensitive system, I would say. Don't ask me how it is made of, because I have no idea, but it is very sensitive, and this measuring the little dust particles that will impact, hopefully, with the CubeSat. And this is to solve for the problem of understanding if there is a cloud of dust even all around the asteroids, because on comets it's straightforward, but on asteroid you can have little particles that orbit the asteroid, for instance, which you cannot detect unless you have this very precise instrument. And this is designed and developed in Italy. While the other spectrometer, the one that I was referring earlier, has other requirements in terms of observation of the crater. So point is that the system has the D2, so the little asteroid, has a circular orbit around D1, or is thought to revolve in circular orbit around D1. Moreover, there is the assumption that the moon is in a 1-to-1 spin orbit resonance, like our moon, is in resonance with its orbital motion, and we always see the same side of the moon, okay, the near side. Now the same appears, the same is assumed for the little moon around the big asteroid, which means that if you have a crater, that you want to look at, this crater is revolving, is rotating, okay, on around the moon spin axis in the same fashion as the orbital motion. And this is quite hard because it's imposing very specific geometry, observation geometry, and we are studying this problem, and we have identified a geometry that blocks the problem, and some points that we are calling key points, where you have to fly through these points, and when you're flying in this key point region, you have to take this kind of measurement. So the answer to your question is that there are no other instruments that are affecting the trade-off, but however, it's the same instrument, but other kind of measurements that are actually strongly affecting the trade-off.
So does the DART mission know at what point on the surface of Dimorphos, the moon, they're going to impact? Because that will also affect.
Yes, we are. Yes, we are assuming. Of course, there is a tight cooperation between the two agencies, and the baseline is to aim to the leading side of the moon. So the side that is aligned with the velocity vector of the moon. Okay, so the assumption that we are making is that the crater will be at on the hemisphere that belongs to the leading side of the moon.
Okay. So then, now that we've gone through the closed orbits, can we then get to the hyperbolic arcs that you guys decided on this trade? That's going to be what you're going to be moving forward with?
Yes. So these arcs are called safely hyperbolic arcs, because the issue is that if you by chance or by mistake you miss a maneuver, it's inherently safe. It means that in the worst case, you will get away, you will move away from the system, but eventually you will not impact with either of the two asteroids. So it's inherently safe in this sense, because they are open orbits, okay? And we perform some sort of back and forth motion on jumping from one hyperbola to another, and to another. That's why we went for this kind of inherently safe orbit for the Milani design. Of course, there are no free meals, so this inherently safe solution comes at a cost. The price to pay for this is that at every maneuver point you have to reverse the velocity vector. But fortunately, we are talking about extremely weak gravitational environment, so extremely weak vector fields. So at the end of the day, this can be done with almost no problem. We are accomplishing an entire mission with a delta V budget of, I mean, just to give you numbers, because I cannot give you the exact number since the design is fluid and this is changing. So a number between 5 and 10 meter per second is the total delta V budget for Milani, which is ridiculously low if you think of typical space mission, deep space missions. So you have to maneuver frequently, but you are in low gravity environments, so maneuvers are quite easy to accomplish and cheap.
So I'm wondering, again, a little bit going back into the certainty of orbit determination, where you have these delta V's maneuvers on these hyperbolic arcs that are so small. If I remember correctly, maybe somewhere in the range of centimeters per second. Exactly. So I'm wondering if, first of all, what hardware, I know this isn't your side of the field, but on the hardware requirement side, what is the mechanism that's doing that delta V, like a cold gas thruster? And how do you measure, okay, we moved centimeters per second?
Sure, sure. So the first part of the question, yes, we use a propulsion system that assures 6 degrees of freedom control. So it's made of a number of different little nozzles in the corners of the CubeSat that can exert either a force or a torque or both of them. So in principle, you don't even have to repoint the CubeSat along the desired position, but you can, even by locking the asteroids in the field of view, you can have translational motion by a suitably defined combination of the little thrusters that you have in the corners. Second part of your question is how you're going to measure this. Well, we are thinking of using an accelerometer on board. Okay. And the idea is to take samples across the maneuver, to download this information on ground, and as part of the orbit determination that is done on ground, together with radiometric data, pictures, LiDAR that I mentioned earlier, one has to also consider the data coming from the accelerometer.
Okay. And one of the things on these hyperbolic arcs that you mentioned that is, it's safer than the other ones because if you miss maneuvers, it's okay. And I'm wondering, in the paper, there was also some talk about entering chaotic three-body dynamics. So does that go back into kind of how you can model the system as a circular with restricted three-body problem plus solar radiation pressure? So yeah, what kind of chaotic three-body motion was being referred to there?
That part refers to the typical orbits that you can have in the CRTBP that are not Lagrange point orbits. For instance, you can have another kind of orbits that are quite famous in the literature are these DROs, so distant retrograde orbits, or other kind of similar orbits, which means that you have periodic orbits that take into account two simultaneous gravitational attractions on the CubeSat itself. So the one from the main asteroid and the one from the little moon. Again, these orbits were deemed too much unstable, and they were not considered, and they were discarded because the inherently safe hyperbolic arcs were deemed most suitable. I want to mention about the SRP, the solar radiation pressure that you mentioned. I said that this is an extremely weak gravitational environment. It is so weak that the SRP is the leading, above certain altitude, the solar radiation pressure is the leading force, is the leading acceleration. So if you do not maneuver, it will swipe out the CubeSat from the environment. It's some sort of self-cleaning environment. If you don't maneuver, you will be pushed away from the solar radiation pressure that you have there. So I mean, I wanted to follow up what you said, saying that it's a perturbation. It's usually thought as a perturbation, is something that you can cancel out. But in this environment, is not only a perturbation, is the main component of the right-hand side.
So we're at 9:31 right now. Do you have to go now? Yep. Okay. No worries. We can just cut it here, and then we can. If you have some other time, that'd be great.
Let me. Yeah, because I mean it's 5:30, and I will finish at 7 p.m. here, and I think for today I'm done.
Oh yeah, no worries.
Tomorrow same time.
Yeah, I could do that. Let's do tomorrow. Okay. Cool.
Okay. Are you sending
Yeah, I'll go
Another
ahead.
link, or can we?
I'll just send another link. I can just email you.
Sure. Sorry about that.
Hey,
It's very pleasant conversation, but I made a mess with my agenda. Sorry about that.
Yeah, no worries at all. Thank you for taking the time in the first place.
Talk to you tomorrow.
Okay. Bye.
All right. Bye-bye.